Our talk today is about storage in AI use cases, particularly in cloud and virtualized environments. So this is something that our team has been working quite a lot with. And we've seen that there is a particular, let's say, challenge when it comes to AI workloads in the cloud, as the data pipeline is often using, let's say, different types of workloads throughout the data pipeline, right? And when you have such different workloads throughout the data pipeline, you often see traditional software-defined storage solutions struggle, as they're often tuned for one or the other particular workload. And in this case, we see workloads that are kind of small I/O. Often we see workloads that are large file operations. And in this case, traditional software-defined storage solutions can have some challenges. And we've also seen cases where there's a significant loss in performance due to the virtualization technology and interactions in of itself. So NVIDIA has recently shared some data around GPU utilization. And we see that during checkpoint operations or during data loading, the GPU cluster is often idle. But during those particular operations, we see that the storage system often has loads in the tens of gigabytes per second. And again, this is often a mix of small I/O and large files. So both types of performance are really important. So what goals did we have when kind of building our solutions and when testing solutions for the, let's say, cloud environments and for AI workloads in these cloud environments? We wanted to develop our high-performance block storage, shared storage solution. And the goal was really to deliver sustained performance of tens of gigabytes per second, both on small I/O and on large workloads in virtualized environments when working underneath a parallel file system. Our goal was also to minimize the resource usage and to be really efficient as possible in terms of the requirements for the virtual infrastructure for the virtual machines. And we also wanted to reduce the complexity in terms of the integration, administration of the environment as a whole of the solution. So what we developed at our core, so the core of our solution is called Xyrate Opus. So this is a proprietary software RAID engine that's developed by our team. And essentially it builds a secure volume over local or disaggregated drives. It's entirely in the user space, and I mean, it can be deployed bare metal in virtual appliances or on DPUs. But at its core, the focus is performance. And here we have some test numbers that we did with Kioxia. And you can see that with 2 RAID 5 volumes, we're able to actually reach 100% of the theoretical performance that the system can do with our solution. So if we compare the theoretical in terms of 4K random, write and read, we're actually able to match that performance. And then if we look at sequential read and write, we're also able to reach over 90% efficiency. So this is some really impressive numbers. We actually haven't seen anything come close to these numbers overall. Here's a quick architecture diagram of our solution. So yeah, we have our own RAID calculation engine, NVMe over Fabric initiator, and many other components that our team has developed. So then we looked at the most efficient method of passing or delivering a block device in virtual environments. So we looked at VirtIO, we looked at vhost-user-blk, we looked at ublk, vDeuce. So ublk was essentially eliminated straight away as it has very limited support for virtualized environments. And then our focus was on vhost-user-blk more than anything in the end. So it allows essentially to pass block devices to virtual machines. It works in the user space. It's quite high performance because it uses zero copy. But then we had to actually modify in the end the vhost-user-blk to add multi-threading support, which is right now only available with Zinor. And we significantly were able to boost the performance of vhost-user-blk. So on the other hand, there's also vDeuce, which is also a technology that allows the creation of VirtIO devices in user space and present them to virtual machines through the VDPA mechanism. So yeah, essentially it enables block devices to operate with high performance and low latency. So we did some tests comparing Xyrate Opus, so our block device solution, in RAID 5 with 24 drives versus MD RAID and RAID 0. So this is a single virtual machine running Rocky Linux. And yeah, here's the random read performance. So again, keep in mind that Xyrate Opus is working with RAID 5 and MD RAID with vDoS and VirtIO is working with RAID 0. So RAID 0 is the optimal, let's say, performance solution, but it's not realistic for production workloads. If you actually put any kind of parity RAID with MD RAID, then the performance gap between Xyrate Opus and MD RAID would be much bigger. And as you can see in all the different benchmarks, Xyrate has significantly outperformed MD RAID. So yeah, this is continuing with now sequential writes. And then we also compared the network protocols with Opus. So Xyrate Opus with vhost-user-blk, with NVMe over Fabric, with RDMA and TCP. And we can see that vhost-user-blk is generally equal to NVMe over RDMA, and NVMe over RDMA is very efficient. So it's obviously limited by the network. It's easily able to saturate 200 gigabit network. TCP is not. TCP is not the optimal solution here. But both NVMe over RDMA and vhost-user-blk are performant, but NVMe over RDMA is clearly network limited. So what was our conclusion out of this work that we did here? So it's that Opus is a good solution together with vhost-user-blk to deliver the high-performance block device to virtual machines. And that's the solution that we opted to go with in the end. So we developed a multi-threading interface here. We reused a lot of best practices from SPDK. We optimized the solution to use specific features of AMD and Intel x86 CPUs. And we optimized the performance so that the performance is available for a single virtual machine and a single block device, and then it scales out very, very linearly from there. So even on the smallest installations, you're really able to take full advantage of the performance capabilities. Then we took a look at how we can accelerate parallel file systems in the cloud, specifically for AI use cases again. So we have a long history of working with Lustre. I mean, today Xinor has tens of deployments in production with Lustre in various capacities. And yeah, today we also have a solution that enables the deployment of Lustre in virtualized environments. So here you can see on the left side, you can see Xyrate Opus is being used for the block level for the shared storage. But then we also have a highly customized OSS and MDS servers that are customized and tuned by Xinor in order to enable this, the use of Lustre in virtualized environments. And both of these solutions here, so we also tested PNFS, they're based on disaggregated storage resources, out of which we are creating the high performance volumes using Xyrate Opus, and then we're passing them onto the virtual machines. And the PNFS, it's using the block layout, and the rest of the idea there is based on the fact that we can interact directly from the virtual machines with Xyrate Opus block volumes. And we use the PNFS MDS server in order to ensure scalability. So yeah, as I mentioned here, we are creating the block volumes out of the disaggregated storage resources and using the modified vhost-user-blk to pass them through to virtual machines, which are operating as Lustre OSS and MDS servers. And then in turn, the parallel file system is being exported to the client virtual machines using the Lustre client. Here's the test setup that we had. What's important to note here is that firstly we're using RAID 6 on both the OSS servers and then RAID 1 on the MDS server. And the aggregate drive performance per node, so we have two OSS nodes here. So per node is 9 million random read IOPS, 3 million random write IOPS, and 70 gigabytes per second of sequential read and write performance. So the Lustre performance here in terms of with Xyrate Opus and without Xyrate Opus, we can see that it is significantly faster on the random operations, and on sequential operations, it is on par. It is being limited by the network in this case. So here, the Lustre without Xyrate Opus is using MD RAID 0. So again, this is a very utopic scenario for MD RAID and wouldn't be actually used in production. So with any kind of RAID 5, RAID 6 with parity RAID, the performance would be significantly worse for MD RAID, and the gap in performance would be a lot larger on both random and sequential performance. So then we have to admit that, Lustre is a complex system. So we actually looked at ways how we can reduce the administration burden and the complexity of Lustre. So we actually turned and tested vfio-FS to be specific, which is actually quite commonly today adopted by cloud providers for a variety of use cases. So the key advantage of vfio-FS is the ability to share the host's file system directly to virtual machines, eliminating the need for additional software installation or configuration within the virtual machines. So vfio, it has the daemon side on the host side, and then it has the client in the virtual machine. Both of these are communicating using the vfio framework, and they're working in user space. So here we have the performance results of our vfio testing. So without any kind of tuning, vfio is not performant. It really slows down the system, so it's only showing like 7 gigabytes per second of sequential performance. But once our team has actually put a lot of effort into tuning and customizing vfio-FS, we were able to also saturate the network and see the same results as the native Lustre client performance that we showed earlier. However, when it comes to random operations, vfio has significant issues and also has a significant resource overhead that is just not scalable. So what are the outcomes? Well, we can see that even with just 2 OSS nodes, Lustre can actually deliver really strong both sequential and random performance in these kind of environments. And but it's very essential, very critical to have a very fast block device that can be passed through to the OSS and MDS virtual machines. And Xyrate Opus is really a good solution that is able to eliminate any kind of bottlenecks in this case. And of course, there is a certain complexity that comes with Lustre. However, vfio-FS can reduce this complexity if you're looking mainly for sequential workload patterns as part of what you're doing, which might not be the case for AI. So one of the things that we wanted to also mention is that we've been working a lot with PNFS, and this is one of our visions for the future. So the PNFS block layout, it became part of PNFS as part of the extension in NFS 4.1, and it's designed essentially to enable the parallel access to the storage devices, and it significantly improves the scalability and performance. So we've been using this architecture. It's the same hardware as was used in the Lustre testing earlier that we showed. And here we're creating 2 RAID 6 volumes. And here's the performance of PNFS with and without Xyrate Opus. So without Xyrate Opus, we're coming back to MD RAID in RAID 0. So we're showing significantly better performance with Xyrate Opus, both on sequential and on random performance. And here we're comparing PNFS versus Lustre. So the sequential numbers for both write and read are on par, very, very similar performance overall. But on the random performance, it's interesting to see that with lower I/O depth, PNFS actually has a significant performance advantage compared to Lustre. So what's our conclusion here? Well, we believe that PNFS has the potential to be the best option with proper configuration. It is very, very scalable and very performant, and it has really minimal latency, so it can actually offer really good performance in both sequential workloads and random workloads, and can be potentially a very good solution for virtualized environments with the cloud use cases. However, it does have its drawback that we believe the open source MDS server today is not really production ready. So it's okay for POCs, but to use it in mass scale production could be very challenging. So yeah, right now we're actually looking and working with some partners to continue PNFS development and hopefully make it a production ready solution. So what are our conclusions? Our conclusions are that Xyrate Opus and Xyrate Lustre solution are both ready today and can be actually deployed in cloud environments for AI use cases. And they are showing really good performance. So we're working with our customers on various use cases in virtualized environments. And we've been seeing really good success once we've also adopted and modified the vhost-user-blk with multi-thread threading. Yeah, thank you. This is our presentation. You can download the slides using that QR code, and we'd be happy to answer any questions that you guys may have. Go ahead, sir.
You mentioned using some of the CPU features. So can you talk about what kind of hyper acceleration you're using, and also what the CPU utilization is for anything?
So in terms of CPU features, we use, for example, AVX technology of x86 CPUs that are available with Intel and AMD server-grade processors. But we also support ARM, so it's not let's say critical to the performance. And for where do we have this? So here the virtual machines with OSS and MDS were assigned 3 virtual cores, and each storage controller was assigned just 1 CPU core. So Xyrate Opus was using just a single CPU core, and then the OSS virtual machines and the MDS were using 3 virtual cores. So the performance overhead in this solution is very minimal. So it's as lean as it can basically get. So the block device is actually using just 1 CPU core.
And the right of this is polling bank, so we require separate calls.
Yeah.
Require a few calls.
Yeah, so the CPU core is entirely dedicated to that process, but you only need a few, like 1 in this case, maybe a bit more in other use cases, so it depends, but it's very lean.
And when you're dealing with AMD CPU, you should understand that it's better to have the rate of instances and VM instances on the same chiplet with the better performance, but the better CPU utilization. Better latency. So that's what we developed efforts to find the right way to place CPU cores required for Opus and CPU cores required for virtual machines.
Yeah, go ahead.
Sorry, I came in a little late. Do you have these little chip sleeves on your work background?
Yes, this is entirely software. It's 2 times 200 gig. Fully saturated. So our solution here, basically, with Xyrate Opus. Yeah, so there's,
Okay, the bottleneck is, okay, got it.
yeah, so 32 jobs, so 32 streams.
Got it, okay.
Yeah.
And that's impressive. Very good. I think that is very good.
Yeah, basically, yeah, Xyrate Opus is saturating the network quite easily with these benchmarks, and yeah, we've done testing on bigger networks, and it's able to saturate them as well. So as I said, here the Xyrate Opus particularly is using one CPU core entirely, so the entirety of a single CPU core. So there's two volumes there, so each volume is using single CPU core entirely. And then it depends, it goes up and down on that CPU core, but that's it. Okay, well, any other questions? Yeah, go ahead, sir. Yes. What we did different from the multi-threading in the vhost-user-blk.
Our software based on SDK and SDK doesn't support multi-threading for because we tried to limit, but for now it was found by Intel. The main issue is that when you are dealing with multi-threading, you should take care of data consistency and other main players like volume manager, rate engine. I understand that about multi-threading environment, we also can share the same device or different protocols. Now we can share the same device or vhost-user-blk or NVMe RDMA NVMe TCP at the same time without data consistency loss. And at the moment we are working on vfio-usr server and some installations like container we create local block device and looks like vfio-usr is the best.
Yeah.
We took care about underlying levels like
All right, any other questions? No? Okay, thank you.